Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will demonstrate the shooting method of solving differential equations for boundary value problems. So, while solving differential equations, mostly we are given initial conditions, and it is easy to solve such ODEs when we are given initial conditions. But if we are given boundary conditions, then it is difficult to solve such a differential equation, because in that case the initial value or initial condition has to be assumed first, and by hit and trial method the initial condition is selected and specified such that the boundary condition is satisfied, right? So in boundary value problems we are given the boundary condition, not the initial condition. But differential equation is solved using the initial condition. So by hit and trial method, we have to adjust the initial condition such that the boundary condition is satisfied. Then our differential equation will be solved completely. Okay, so this is done by assuming initial values that would have been given if the ODE were an initial value problem. The boundary value obtained is then compared with the actual boundary value using trial and error or some scientific approach. One tries to get as close to the boundary value as possible. For example, if we are given a cantilever uniformly loaded beam, and to find the deflection V as a function of location x due to a uniform load Q, the ODE that needs to be solved is this. So L is the length of the beam, and now consider a similar beam problem where the beam is simply supported on the two ends. To find the deflection V as a function of x due to the uniform load Q, the ordinary differential equation that needs to be solved is given in 13.2. So in this case, we will be given V at 0 and derivative of V with respect to x at 0, and both are given as 0 because at this point the deflection is 0, right? And also at this point the derivative of the deflection is also equal to 0. But if this cantilever is supported at the two ends, then we have to solve such a differential equation. And in this case, we will be given two conditions. One is V is at 0 is equal to 0, and the other one is V at L is equal to 0, right? At this point, the deflection will also be equal to 0. So we are given two boundary conditions. And here, in this case, we were given two initial conditions, V at 0 and derivative of V at 0. So this becomes a boundary value problem, right? So while solving such differential equation, we have to satisfy these two conditions. So while solving such differential equations, this is the flow chart, and we have to define H, we have to define coefficients A1 and A2. We have to first initial guess or define the initial condition, solve the ODE, and we have to compare the boundary value with the final value of the solution. And if they are not equal, there will be an error. And if the error is a positive, we have to decrease the initial condition, and if the error is negative, we have to increase the initial condition. But if they are close enough such that their difference is smaller than the tolerance, then we can say that x naught is the required initial condition. So this is a hit and trial method, and we have to use the initial guess first, and then we have to solve this differential equation repeatedly by adjusting the initial condition. And when we see that our final value is equal to the boundary value, then that initial condition will be finalized and the whole differential equation will be solved. So for this purpose, I have considered the same differential equation which I considered in my previous lecture. So that differential equation is also written over here, and this differential equation will be solved numerically uh, using Range and Kuta method, which we discussed in the previous lecture. And now we will specify the boundary condition, and we will see if that boundary condition is fulfilled or not. Okay, so this is the step size which we have specified, right? And this is our time span. These are our a1 and a2 values which are specific for the Hume's method. And we have specified the boundary value of theta as 650, and we can change it as well. First, initially we have specified the initial condition as 1200, and then we will use this algorithm, right? So this algorithm, this command of MATLAB will evaluate the actual initial value or initial condition of solving this differential equation that specifies or that determines our boundary value, right? That guarantees that our boundary value has been achieved. So this is another file, and in this file we have to write a user-defined function, and I have named this function as myfunc, and this is the outcome of this function, which is z, and I will pass these variables. This is the initial guess, this is the boundary value that has to be achieved, this is the step size, this is time vector, these are a1 and a2, and theta, the initial value of theta is actually the guess, and I will consider this for loop using range and quota method. Okay, these are my k1 and k2, and they will be uh, input over here, and I will evaluate theta I plus 1. The for a whole span of the time, this equation will be solved, and at the end I will take the difference between the boundary value which has to be achieved and the final value of solve after solving this differential equation. So the final value of theta after solving this differential equation will be compared with my boundary condition, and that z must be minimized. So if that z is equal to 0, so that value of the initial condition will be the final value. Okay, so now this function will be called in this MATLAB command, and in this MATLAB command, it will give the initial guess which actually satisfies the boundary condition, and that initial guess will be stored in this vector, okay, in this variable guess solved. So this guess solved will be considered as the initial condition. Now I will solve the same differential equation to plot my result. Okay, so I have specified the final value as 650. Now let's run this code, and you can also see that I am passing this at my function. So this user defined function is actually called in this line. Okay, so this will give me the actual initial condition that will satisfy my boundary condition. So you can see that guess solved is this value 1227.1, and if I specify this as the initial condition, then my boundary condition will be equal to 650. So I have specified boundary condition as 650, and you can see that the differential equation has been solved, and this initial condition has been adjusted by the solver such that the boundary condition has been met. So let's change this initial condition to 600 now and run this file again. So again, this has changed the initial condition such that the boundary condition has been achieved. So this is how we can apply shooting method to solve boundary value problems and solve the differential equations. So I have done the same thing over here in this manual, and you can try this thing by yourself as well. And I hope you have understood the concept of shooting method in solving boundary value problems. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.